So now we're back to Kaggle's Intermediate Machine Learning, Categorical Variables. So there's a lot of non-numeric data out there, and here's how to use it for machine learning. All right, so this one's going to be kind of a little bit painful, but we're at that point. So let's go. So in this tutorial, we're going to learn what a categorical variable is, along with 3 approaches for handling this type of data, okay? So here's the introduction. A categorical variable takes only a limited number of values. Consider a survey that asks how often we eat breakfast and provides 4 options: never, rarely, most days, or every day. In this case, the data is categorical because responses fall into a fixed set of categories. True. If people responded to a survey about what brand of car they owned, the responses would fall into categories like Honda, Toyota, Ford. And in this case, the data is also categorical. Turns out. All right. So we're going to get an error if we try to plug these variables into most machine learning models in Python without pre-processing them first. Yeah, because they don't really know what this is. Like, they see the words, but, you know, what does that mean, right? In this tutorial, we're going to compare 3 approaches that we can use to prepare our categorical data. All right. So here's the 3 approaches. The first one is to just drop the categorical variables. All right. So the easiest approach to dealing with categorical variables is to simply remove them from the data set. True. This approach will only work well if the columns did not contain useful information. Also true. So here's the second approach, ordinal encoding. So ordinal encoding assigns each unique value to a different integer. Okay, so we see the breakfast example from up there: every day, never, rarely, most days, never. So these are just random, in random order, whatever. So every day would have the value of 3, never would have 0, rarely would be 1, most days would be 2. So it would go in order from 1, 2, 3, 4, and it would just go down, and the 3 would always equal this, the 0 would always equal this, and whatnot. And that's just in any ordinal encoding example, basically. So this approach assumes an ordering of the categories. Never would be 0, rarely would be 1, most days would be 2, and every day would be 3, and this is greater than this, is greater than this, is greater than this, right? So the assumption makes sense in this example, yes, because there is an indisputable ranking to the categories. Also true. These are definitely in order, in an order of, I guess, ranking, it said, right? Not all categorical variables have a clear ordering in values. True, like the Toyota and the Nissan thing up there, or Ford, whatever. But we refer to those that do as ordinal variables, pardon me. So if it's got a ranking, it's ordinal. For tree-based models like decision trees and random forests, we can expect ordinal encoding to work well with ordinal variables. Okay. So here's the next one, the third one. One-hot encoding. What a name. One-hot encoding creates new columns indicating the presence or absence of each possible value in the original data. To understand this, we're going to work through an example. All right, so we got to go through this because it doesn't explain it that well down here at all. All right, so we got this column, and it's got just these color names in it, right? And we can see it's got 3 different unique color names. It's got red, it's got yellow, and it's got green. Green. And we can see they repeat whenever they want, all right? So for one-hot, what we're going to do is we're going to take these unique variables, these unique variable names or whatever we call them, and we're going to create new columns with each one of the variable names, right? So we've got a column with the red, a column with the yellow, and a column with the green, right? So in this first one, it's red. So red is going to be 1, and yellow and green are going to be 0. 1 is basically true in this instance, right? Because like as we've done in like JavaScript or whatever, whenever you have 0, it's always going to be a whatever the word was, where it's like nothing. It's the same, like a falsy value, and then 1 is a truthy value, right? So red is red, so red is 1, yellow and green are going to be 0. Red's 1 on another red, yellow and green are 0. So this is yellow, so red's going to be 0. It's not it's not yellow. I mean, it's not red. It is yellow. So it's truthy value under yellow, and then another falsy value under green. And then green is going to be 0, 0, 1. So it's not red. It's not yellow. It is green. It's not red. It is yellow. It's not green. And that's basically how this works. And we'll get into what we do with it later. But let's go through this, these few paragraphs. All right. So in the original data set, color is a categorical variable with 3 categories. True. Red, yellow, and green. The corresponding one-hot encoding contains 1 column for each possible value. Red, yellow, and green, right? And 1 row for each row in the original data set. And here's the rows right here. The red, red, yellow, green, yellow, right there. So wherever the original value was red, we put a 1 in the red column. Boom, boom. If the original value was yellow, boom, boom. And if it was, pardon me, where's the green? Oh, and so on, as if there's so many more. Anyway, so we get that. In contrast to ordinal encoding, one-hot encoding does not assume an ordering of the categories. Thus, we can expect this approach to work particularly well if there's no clear ordering in the categorical data. For example, red is neither more nor less than yellow. Yeah, they're just 2 different things. They're not, it's not like red, it's not like it's not like we're going in color spectrum order or anything like this. It's just red and yellow as equal values, all right? So, or equally important values. So we refer to categorical variables without an intrinsic ranking as nominal variables, okay? So these are nominal variables. I don't even remember what we said the other ones were. I guess ordinal variables. Okay, so these ones are ordinal and these ones are nominal. All right, that's probably going to be the last time we see this too for a while. Well, let's get back to it. So one-hot encoding generally does not perform well if the categorical variables take on a large number of values. For example, we generally won't use it for variables taking more than 15 different values. And that's very true because it gets, like you can see right here, we went from 1 column with 5 entries to 3 columns now with 15 entries. Okay, so this is, it multiplied this by 3 right there, okay? So it can get pretty big pretty fast. So here's an example. As in the previous tutorial, we're going to work with the Melbourne housing data, and we're not going to focus on the data loading step. Instead, we can imagine we are at a point where we already have the training and validation data in xtrain, xvalid, ytrain, and yvalid. We're not doing that. We have to look at this because it's completely different. Well, I mean, it's not completely different, but it's different enough to where we need to see it. So we're going to import pandas as PD as usual. We got train test split. We're reading the data in. Separate the target from the predictors. Okay, so we're saying little y is data.price. And then instead of having a features list, we're just saying big X is going to be data.drop. And then we're just going to drop price from it and leave everything else there, right? So now we got a data frame with everything but price, and we've got a series with only the price, right? So now we're going to do a train test split with 80% of the data frame is going to be training, whatever, training data sets, whatever. And then we've got 20% as the test, okay? And then random state 0, we know all about that. All right, so now we're going to drop columns with missing values, all right? So we've done stuff like this before. We've got the columns with missing is going to be call in xtrain full.columns if xtrain full call.isNull.any. So basically, if there are any nulls in the column, we're going to put it inside of this list right here, right? So this is going to be the list with all the column names with missing columns, and then we're going to drop all the columns with missing columns in it. All right, and then we do the in place true, because if we don't do that, it'll make another data frame with the missing columns, which we don't even need that. All right. So now here's the cardinality thing. So cardinality means the number of unique values in a column. We're going to select categorical columns with relatively low cardinality. Convenient, but it's also arbitrary. We can do any number we want, all right? So low cardinality calls equals CNAME for CNAME in xtrain full.column. So it's going to be this thing that's already been dropped, the training that's already been dropped, and the column names. So if the column name inside of here has less than 10 unique values, right? We're going to, and the data type of it is object. So if it's got a string with less than 10 unique values, remember this one had 3 unique values right here. So if it's less than 10, what we're going to do is put it in this list. So this is going to be the list with the less than 10 column names, right? And we also are going to get the numerical columns. So we're going to say CNAME for CNAME in xtrain full dot column. So the columns, if xtrain full CNAME, so if the column name dot type, so if the column's data type is either int64 or float64, we're going to put it in this one. And we're going to have this list with those column names here. And then we're going to say my calls equals low cardinality calls plus numerical calls. So we'll add this one to this one. So this one to this one. And then we're just going to say xtrain is this is the full training data, but only these columns that we picked out dot copy. So now we got some new training data with this and some new validation data with this. And you know, the validation data is pretty much doing the same thing, right? All right. So let's go. So now we're going to take a peek at the training data with the head method below, right? And we can see we've got a bunch of columns with a bunch of numbers in it. And we also have 3 columns with strings in them, all right? So let's go down to the next one. So next we're going to obtain a list of all the categorical variables in the training data, okay? We do this by checking the data type or D type of each column. So the object data type indicates a column that So the object data type indicates a column has text. There are other things that it could theoretically be, but that's unimportant for our purposes because they only have text in this data frame, right? So for this data set, the columns with text indicate categorical variables, right? Basically. So here we go. We're going to get a list of the categorical variables. So we've got S equals xtrain.dtypes equals objects. So S is going to be the data frame of the training data with all the object data types, right? So basically these 3 right here, right? And now that we've got that, we're going to say object calls equals list, and we're going to make a list out of S, and we're going to have S at S equals index. So basically what this is, it's just one of those things where it could be written like this, S where S double equals true, right? We could write that, but since it knows better, we just have to do this. So if it exists, it's going in the list, okay? And then we're going to print the categorical variables, and we're going to print categorical variables colon, and then the object calls. So this is going to give us this list right here with these 3 what are the column names. So we've got type, method, and region name right there. Boom. Pretty easy stuff. Yeah, right. Anyway, so we're going to define a function to measure the quality of each approach, all right? So we're going to define a function score data set, which we've done plenty of times, and this is going to return the may, all right? So we see this, and it's just the same as it's always been, getting the random forest, getting the mean absolute error, and then returning the mean absolute error after all this stuff that we've done plenty of times up to this point, all right? So let's get rid of this, unhide code, whatever. All right, so the may for this one is going to be 175,703. And I can't remember what it used to be. I think we were at like 180 or maybe like 171 or 177. I don't know, but this looks pretty good compared to what we've been doing, right? So now we've got the score from approach 2, and this is going to be the ordinal encoding, okay? So scikit-learn has an ordinal encoder class that can be used to get ordinal encodings. We're going to loop over the categorical variables and apply the ordinal encoder separately to each column, okay? So we've got the ordinal encoder right there, and then we're going to say label train label xtrain equals a copy of the data frame, and then this is going to be a copy of the training data frame, the copy of the validation data frame. And now we're going to apply the ordinal encoder to each column with categorical data. Okay. So ordinal encoder is going to equal that class that we were talking about in the paragraph up there. And then we're going to say label xtrain, the object calls. So any of the columns from this list right here, the object calls list. What we're going to do with that is we're going to say that equals ordinal encoder, so the class thing, dot fit transform, and then we're going to have xtrain object calls. So it's going to do a fit on the data frame with only the object calls columns right there. And then we're going to do the same for the valid, except for, of course, we're going to do this transform because we still haven't figured out why this does fit transform. And maybe one day we'll scoot over to what is it, Gemini, and figure it out, but not today. All right, so we've got that, and then we're going to run the score data set, the May finder, on this, and we can see this is probably the lowest we've seen it so far, 165,936, which is pretty low compared to what we've been seeing in the course so far, right? So there's that. So in the code cell above, for each column, we randomly assign each unique value to a different integer. I guess that's what the fit transform's doing, okay? And this is a common approach that is simpler than providing custom labels, okay? However, we can expect an additional boost in performance if we provide better informed labels for all ordinal variables. What's that mean? I have no idea, and we're not going to go into it either. I've already read this twice so far. So now we've got score from approach 3, the one-hot encoding. So we use the one-hot encoder class from scikit-learn to get one-hot encodings, believe it or not. So there are a number of parameters that that can be used to customize its behavior. That being said, let's grab this. Ooh, I didn't know we could just click that. So let's go over here and look at it after we read this stuff. So we're going to set handle unknown to ignore, and this is going to avoid errors when the validation data contains classes that aren't represented in the training data. And we're going to set sparse to false, ensuring that the encoded columns are returned as numpy array, as a numpy array instead of a sparse matrix. What's that mean? I don't know. But anyway, we do have to look at this over here real quick because something's changed, right? So we can see right here, we've got the handle unknown, the default's error, and then we've also got this sparse output equals true. And as we can see over here, it says sparse. Well, this says sparse output. We come down here, we can see that sparse has changed to sparse output. So this is outdated while we're doing it, right? It is what it is. You know, we've been doing this stuff since Free Code Camp. We know that stuff gets outdated pretty quickly. All right, so there's that. If we want to learn more about it, we can just come over here. Give me a second. I thought I had to sneeze. I might have to in a little bit. Whatever, doesn't matter. Let's go. So to use the encoder, we're going to supply only the categorical columns that we want to be one hot encoded. Okay, so it's going to be the same thing. Just put the object calls on there. For instance, pardon me. To encode the training data, we supply xtrain at object calls dot what? Oh no, this is a period. What? Anyway, so object calls in the code cell below is the list of column names with categorical data. I wonder what that's from, but honestly, who cares? Oh no, this is this and this are related. Okay. So let's read it again. Object calls is the code cell below. Pardon me. Object calls in the code cell below is a list of the column names with categorical data. So xtrain at object calls contains all of the categorical data in the training set. We already knew that. All right, so let's go. So we got this one hot encoder getting imported. We're going to apply one hot encoder to each column with categorical data, right? So we do the thing where we do we're doing the thing where this O encoder equals the one hot encoder class, and then we're doing the handle unknown equals ignore like we did over here because we didn't look at the handle thing. Let's look, see if we can find it. Oh, here it is. We can have error as the default, ignore infrequent if it exists, or warn, whatever those mean, whatever. Anyway, so we're putting this to ignore, and then we're doing sparse, which now is sparse output as false, all right? So now O calls train equals the date. We're making a data frame out of this class that we're fitting it and transforming xtrain dot object calls. So we're going to change the data frame with the object columns into the numbers, like we said on the other one, right? And that's what this is doing. And then we're going to do the same thing with the validation data frame as well, right? So now we've got one hot encoding removing so the one hot encoding removed the index, and so now we're going to put it back. So like on the other one, on the one from the last lesson, we were removing like column names. Now we're going to have to now it removes the indexes, and we got to put them back. So now ocalls train.index now equals xtrain.index. So whatever the index was on this, which was nothing, is now what the index is on this one, right? And the same with the validation data. Excellent. So now we're going to remove the categorical columns, and this is going to replace, and then we're going to replace it with one hot encoding. Huh? Oh, yeah. So we've got the numbers. We're taking the object columns out of the training data, and we're just going to be left with the numbers. So we're only going to be left with these columns right here on that one, all right? Let's come back down here. All right, so that's what this one. This is going to make the numbers, and this is going to be OXTrain, and this is going to add the one hot encoded columns to the numerical features, right? So we're going to concatenate in this new data frame the numXtrain and the ocalls train. So we're putting this, we're putting these with these, right? And then these with these, right? So that's what these two are doing. And then we're going to ensure all columns have string type. So we're just going to say OXTrain, which is this thing Oh, yeah. So we're going to make sure this thing.columns now has as type string. So all of the columns are now going to have strings. So even the numbers? Whatever. Anyway, so then we're going to print the May, and we're going to do the score data set on this one. We're going to print the score data set with the OXTrain and the OXValid, and we can see the May is a little bit over. It's a little bit more than this one, but only by less than 100, or a little bit more than 100, right? Because this is 89 and the other one was like 36 or whatever. So yeah, it's just a little bit more than 100 more, which in a number this big, that's pennies, right? That's even less than pennies. The pennies would be here, right? So yeah, it's like 1/10 of a penny. So which approach is best? In this case, dropping the categorical columns, or approach 1, performed worse, since it had the highest May score. True. As for the other two approaches, since the return May scores are so close in value, there doesn't appear to be any meaningful benefit to one over the other. Okay. But in general, one hot encoding, so approach 3, will typically perform best, which it didn't in our case, but we've been tricked before by these guys. And dropping the categorical columns, approach 1 typically performs worse, but it varies on a case-by-case basis. And since it's only 3 things, we can just run the thing with 3 different methods, right? No big deal. That's part of our due diligence when we're earning money, right? So here's the conclusion. The world is filled with categorical data. We will be much more effective data scientists if we know how to use this common data type. I believe it, honestly. So here's our turn. We're going to put our new skills to work, in the next exercise. All right. Give it a second. You know how long this thing takes. So there we go. All right. So now we're on to exercise categorical variables, and we'll see you next time.